action. All right, ladies and gentlemen, welcome. We're talking about the continuity test, and we're on page 166 of our text. Is that right? Yes, we are. Wow. And I'm interested to figure out, is this function continuous at the point x equals 1? And I have to justify it in a number of ways. Well, I think that they would have accepted either way in any case. But let's graph the line 2x plus 1. So when graphing that, that would have a y-intercept of 1 and a slope of 2, so it would be up 2 over 1, up 2 over 1, right? Or down 2 over 1 in the other direction. And my line would look like this. And let's graph negative x squared plus 4 is the way I would write that, by the way. This one, negative x squared plus 4. And using our families of functions talents, could you describe how that's different from a regularly shaped parabola? It's upside down. What's the plus 4 do? It shifts it up 4 units. So I would go, let's see. Let's actually, I guess, mark some tick marks here. 1, 2, 3, 4. Right. 1, 2, 1, 2. And so our parabola has a vertex at 4 on the y-axis. It opens down, so it'd be down 1 over 1, then down 3 over 1, and then down 5 over 1. And it would be mirrored in both directions. Right, something like this. So my parabola would look like so. That's ugliness. Well, whatever. So that's my parabola. Now, since this is a piecewise function, when x is greater than or equal to 1, it is the line. Actually, I might use a different color. I might use our purple or pinkish color. All right, so it is this part when it's greater than or equal to 1, and when it's less than or equal to 1, it's this parabola. So that's what the function looks like. And now the question is it continuous at the point x equals 1? All right there. So graphically speaking, does this curve exist at x equals 1?
No.
Or this function, does it exist?
No.
No?
Yes.
Yeah, it exists. There's not an that wasn't an asymptote that I was drawing, my bad, if that was the confusion.
No, you said the curve.
Well, this whole thing I could refer to as a bit of a curve, I guess. But I guess I see what you're saying. If you're referring to the curve as the parabola is not defined at that point. But the line is. So, yeah, f of 1 is equal to what? 3. So it passes that part of the continuity test. Part 2 of the continuity test, is it approaching the same number from both sides? So from the left, this is approaching 3, and from the right, this is approaching 3. So that appears to be true.
That was also 3.
And then the last part is the value that it's approaching from left and right the same as the value that it is at that point? And that is also true because it's approaching 3 from both sides. So that's kind of a visual approach. Let's do it algebraically. Same concept. So does it exist at f of x equals 1? Or sorry, f of 1. So f of 1 I would plug into the top part because x is greater than or equal to 1. So 2 times 1 plus 1 is 2 plus 1 or 3. And then for the function approaching it, I guess from left and right, I could plug in like 2.99 and 3.01 or something like that if I wanted. Technically, I'd have to plug in a few more values to verify that it was approaching certain things. But if I plug in,
it wasn't just like cutting really close.
Yeah. So if I plug in 2.99, what part do I plug it in? Or sorry, not 2.99. My bad. 0.99. I was thrown off by the 3. 0.99. My apologies. I want to be approaching the 1 from the x. So which function does this apply to? Top, bottom? The bottom one. So that's going to equal 4 minus 0.99 squared.
Which is a new really nasty number.
0.99 squared is something, and 4 minus it is 3.0199. And then let's figure out what is f of 1.01. So what happens when I'm approaching it from the right? So when I approach it from the right, which function is it? According to this, 1.01 is bigger than or equal to 1, so it would be the top function. Approaching it from the right on the graph, it'd be the line function as well. 2 times 1.01 plus 1, bless you. Right, so that's 2.02 plus 1. So 3.02, bless you indeed. Delay there. That was stream lag. So it appears as though this is getting closer to 3. This is getting closer to 3. Oddly enough, both of these are approaching 3 from the top, which isn't usually the case. Usually one's approaching from the bottom. But they do appear to both be approaching the same number, so 2 seems to work out. And then 3 would also work out. So cha-ching, cha-ching, and cha-ching. So it does pass the continuity test both visually and algebraically.
Yeah, for the second part, I just made a table and put in a few values that were surrounding the given x value.
Yeah. Yep.
To see if they seem to.
That's
converge.
perfect. Yeah. So that's what if I did make a table and plug in some more numbers here, that'd be good too. And as far as like doing this on a calculator, I don't remember how to do piecewise functions on a calculator, but you could plug in both and then just remember which one applies in which domain, and then you'd be fine. So other questions, what do we got? Blurries. 27. So it says graph each function, determine which intervals the function is increasing and decreasing. So, first of all, what type of function is this? A trinomial? A cubic trinomial. It's a type of polynomial function. Is this function continuous?
Yes.
Yes, it's continuous everywhere. All polynomial functions are continuous all over the place. So if I wanted to... What?
It's
Yeah, so, I mean, as long as there's like no negative exponents or weird things like that, yeah, regular polynomial. Made up of terms, single variable. Yeah, good stuff. So, to graph this, I guess that would be a little bit of work. I would say we should probably either make a table or use technology. In this case, I'm going to do both, making a table using technology. I wonder if I can quickly open up an Excel spreadsheet. Let's see. There's my continuity test one. That's not quite what I'd need. Actually, I think what I could do is make a copy of this. Copy the sheet. Copy, copy. And on this sheet, I'm going to, instead of having these values here, what if, let's see, how do I have this defined? That's equal to B1, and erroneous. And this I'd want just to equal B1 minus 1. And then, well, actually I could $sign that. Or I could just have it be B9, actually. Benign. Oh, A9 is what I meant. That's what I meant. And then drag this up. And this would equal A9 plus 1. I'm just trying to make it so it does a table of values for us a little bit. And our function is not that. It is negative a3 to the third power, right? So negative x cubed minus 2a3, or times a3 maybe would be better, plus 1. And then I'll drag this down like so. And I'll snapshot this, and then we'll analyze. Analyze, analysis. So there's the table, and we'll talk about monotonicity both from a table perspective and we'll do it from a graphical perspective. So I mean, I could go through and draw my own graph and plot all these points. I'm just going to quickly make it on this. Oh, that's not what I meant. I meant to Command G and graph. So let's see. Let's graph on this negative x cubed minus 2x plus 1. Bam. So there's our graph. And I might want a rectangular grid. Do I already have that? No, I don't. Rectangular grid. Here we go. So, because I can't quite see if this ever changes. So it looks like it's kind of doing the same thing all over the place here, if I'm not mistaken. And I'll just make that line thick. So graphically, if I asked you about the monotonicity, where it is increasing and decreasing, what would you say? For what intervals is it increasing?
None.
Yeah, it looks like none to me. And the end behavior of a polynomial, it usually goes off to infinity, or it always does in some direction. So I didn't anticipate there'd be any other bends that I had to account for. Especially this was a third degree function, so at most it was going to have 2 bends anyway. And you can kind of see it started a bend and then it started kind of bending, but that wasn't necessarily a critical point or an extrema that had occurred there. So there's no point at which it's increasing and it's decreasing always. So negative infinity less than x less than infinity. Something like that is where it's decreasing. So it's always decreasing. Graphically, or sorry, chart-wise, analyzing the chart, notice this is going down, this is going down, this is going down, this is going down. These are all getting less and less and less and less and less forever. Now, the rate at which they get less changes.
What are the numbers on the bottom, like the negative version of 2 less than the positive number?
The negative version.
Yes, you can go like negative 6 and 6.
Yeah.
It's 229 and negative 227.
Because 0 is at 1, not at 0.
Well, yeah, I think it's partially because it was shifted. It's not a symmetric graph about the origin or anything like that.
X-intercept is,
Yeah,
or
you can.
Y-intercept is 1.
Yeah, so it's been shifted, and then also this minus 2x has an effect on it. But yeah, and actually 134 and 136, well, those are 2 away. 73, 71, those are 2. Yeah, it does seem to be somewhat consistently 2 units away. Yeah, interesting. But yeah, so this is always decreasing. So if I was describing the monotonicity, those are the intervals for which it is decreasing. Want me to look at another one of those, or what do you like? What do you like? What is your preference? How can I? 29? 29 is pretty awesome. I might talk about 29 in a couple of perspectives. So let's graph 29. Actually, before I do, What could you tell me about 29? It has a restricted domain. I don't know if you know that.
What do you know what that means?
That there are some input values that break the function. What x value would just never ever work on this?
2.
2. Why is that?
Because 2 minus 2 is 0 and you can't divide by 0.
Right? So this has a denominator. Denominators can never be 0 because that's dividing by 0. When is this denominator equal to 0? When x equals 2. All right, so that's a restricted domain. The range, actually the range might be a little bit more deceptive.
What about
Negative 2 would be fine because negative 2 minus 2 is negative 4. I can divide by a negative 4.
Oh,
Right. Unless it was, if this was an x squared down here, that would have worked.
And minus.
The range is, this function is not going to be horizontally or vertically asymptotic, but let's see what happens. The range I'm anticipating is going to be going, possibly from negative infinity to positive infinity, although that square might change things a little bit. So if I graph this, let's do this. I will have x squared plus 5, all in parentheses, divided by x minus 2. Notice the parentheses are needed in order to suggest the vinculum covers the right spots there, right? Yes. And if I graph this, I believe this is a diagonally asymptotic graph, but that's not important.
It's rather strange. It's like a hyperbola.
Ish. It's it's somewhat related to the family of hyperbolas, I'd say. Yeah, a little bit. So, looking at this, where is this increasing? Look at this graph. So it's going uphill. Actually, let me do a darker green. Uphill, 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 uphill. Then it stops going uphill. And then it's
x is either greater than 5 or less than negative 1.
And then it looks like it's decreasing.
No, greater than 4.
Here it's decreasing,
Less
and here it's decreasing. So for the monotonicity, it is. Oh, I guess I'll do increasing first. Bless you. The intervals for which it's increasing are x is less than negative 1 and x is greater than 4.
Actually, it's 5. I looked in the back of the book.
All right. Yeah, that seems reasonable. Right. And it's decreasing over what intervals? From negative 1 less than x less than 5. Right? So that's where it's decreasing. Now, what could you guys tell me about the range of this?
How is it increasing? The x is less than
Oh, Mr. Waddy,
See,
For- decreasing, you forgot to put in that x is either less than 2 or greater than 2.
Well, yeah, I guess, I could have broken this up into two cases. Right, negative 1 is less than x is less than 2, and then 2 is less than x is less than 5 would probably be more accurate to account for the fact that it had that asymptote there.
At 2.
At 2. Now, what about the range? What possible y values did this have?
Negative infinity. 2.
So it's the set of all y. So it definitely goes down to negative infinity. But then it looks like there's kind of like this swath of area that the y values never hit, right? Do you guys see that there?
Yeah.
Like from whatever that minimum is to whatever this maximum is.
It's like 10 and 3. Or 10 and 2.
So yeah, maybe I'll call that.
Negative 2.
Yeah, 10 and
Yeah, so y is less than -2 maybe, and y is greater than, yeah, I could call that 10. Right. So I knew that the end behavior was going to be going off to infinity and -infinity, but I couldn't quite guarantee what the range was because I had a feeling there might have been either some holes in it, or it even could have been like something weird like that on both sides, and maybe it was never negative. Let's actually look at the Excel spreadsheet, this version, and let's talk about continuity as well as end behavior. So plugging this in, this would be A3 squared. So for those of you who need Excel practice, make sure you're following along. Plus 5, close parentheses, divided by, open parentheses, A3 minus 2. So A3, I'm referring to my X value over there, and I hit enter, and then I double click when it's a black plus sign, bam, changes all of those. So notice this one's referring to A7, which is what I'd want it to do. So regarding end behavior, let's talk about this. Actually, you know what? I'm going to do this. Bam. Haha. That'll fit my problem all nicely in here. And I think this will be the last of what we do for this, and a nice little summary of everything. I'll fit it over here. Why not? That's a good enough spot. So regarding end behavior, what would you tell me?
As x approaches infinity, y approaches infinity.
Negative infinity.
Well, he said infinity for both, so he was looking at this. So f of x approaches, well, yeah, I usually start with a negative first. So y is approaching negative infinity as x approaches negative infinity. All right. Graphically speaking, that means as x goes to the left, y is going down. All right, that's all that means. That's math speak for that. And then for as x goes towards positive infinity, y appears to be just getting larger and larger and larger. So it appears to be doing that as well. Actually, that appears to have the behaviors of an odd degree polynomial, which would kind of make sense. If I looked just roughly at this and I saw x squared over x, that's going to reduce down to a regular x function or an odd degree. And actually, if I canceled that out algebraically somehow, I think we could even find the equation of the line that it approaches over time for extreme values. But yeah, so it's a diagonal asymptote. And let's actually, because I can, let's talk about continuity at the point 2. Let's see, does it exist at x equals 2, graphically?
No.
No, it does not exist. So it fails part 1 of the continuity test. Does it approach the same value, left and right, of x equals 2? What does it approach from the left? Negative infinity. Uh-oh. And what does it approach from the right? Positive infinity. Uh-oh. So those do not approach the same number. In fact, even if they both approach positive infinity, this would be an infinite discontinuity for this particular value. So it fails part 2, and then part 3 it fails by default because
Failed part 2.
Yeah, it failed part. Yeah,
It failed everything.
it just failed everything. Failed across the board.
So
All right, so it's not continuous. Graphically, you can see that this is approaching negative infinity.
Trying to find it for 2.
That's what I randomly decided. I made up my own question, and it also did not exist at the point. So it failed parts 1, 2, and 3 of the continuity test. There, 1, 2, 3.
Say, Mr. Lottie,
What's up?
I had a thought. If you were standing on a perfectly flat surface with infinite area, what would the horizon look like?
Well, so you're referring to standing on a plane, plane, right? Like put us.
Yeah, like
Right.
yeah, a plane like a flat surface.
Not plain PLAN.
I imagine the horizon would look somewhat flat-ish. Even though, like, typically when in math we draw a plane, we draw it as kind of like a thing like that. Technically, it's going out in all directions, you know, circularly, or so I don't know. I imagine it would look flat-ish.
Maybe you
But-
could look like perfectly straight ahead and see it. It wouldn't
Yeah.
look down at all.
But anyways, so that was our homework on continuity, monotonicity, and behavior. Lots of good stuff.